Hello everyone. Today we will start with the next chapter, which is the chapter that talks about steady state power analysis. Right? But before we do that, there is one final example I want to solve from the AC analysis chapter, which is an example that explores what happens when we have some circuit with two voltage sources or two sources that are of different frequencies. So let's say I have this circuit, 10 ohms and 1 Henry, and then I have two supplies or two sources that are each running at a different frequency. So one of them is running at cosine 10t, right? What's the frequency here? The frequency is just 10 over 2 pi, right? Or the angular frequency is 10 radians per second. And then the other supply is running at 20 radians per second. Right? So how do we analyze this sort of circuit using phasors? Superposition still applies, right? Because I mean, we still have two voltage sources, right? So we can apply superposition. That's fine, but we cannot sum or add phasors directly. So we cannot add phasors of different frequencies directly. Like if I have a phasor 530 degrees that comes from a source that's running at 60 hertz, I cannot directly add it with the phasor, let's say 745 degrees, that's coming from a source that's running at 70 hertz. I cannot add those two phasors directly and expect to get a coherent result or a good result. I can only add phasors together that are of the same underlying frequency, right? But however, what I can do is I can take my circuit and I can apply superposition. I can apply superposition and then analyze the circuit at different frequencies and then do a phasor analysis at different frequencies, right? But then before I sum things back up, I need to go back to the time domain. Before I sum the two superposition domains, I need to go back to the time domain and then do the summing there. So I'll show you how to do that in this example. Right? So in this example, the circuit that I have here can be split into two circuits using superposition. So I can split it into this circuit, which is 100. And I can now, once I've split it, I can change everything to phasors. Right, so I split it into circuit 1, which is 100 cosine 10, which is 100 0 degrees, right? And then this is 10 ohms. What is the inductance? The impedance of the inductance is j omega L. So what's omega? Omega is 10, right? So the impedance here is going to be J10, right? So this is I1 prime, right? And then also now the other part of the circuit is applying superposition, right? So I split the circuit into two parts. The other part is the one I get by applying this source and making the other source equal to 0. So I end up with this other source here. So this is going to be 20, right? So radians per second, but this has a magnitude of 50 and an angle of minus 10. So this is going to be 50 minus 10 degrees. And then again, inductance, resistance. And then now I'm finding this current, I2 prime. The resistance is the same, inductance is also j omega L, but omega right now is 20. So this equals to J20. L is 1 Henry, of course. Right? So between those two superposition circuits, notice that the impedance of the inductance is different because there are frequency is different. Okay, so this circuit, the phasors in this circuit are in the 10 radians per second frequency domain. those are in the impedances in the circuit, and the phasors in the circuit are in the 20 rad per second frequency domain. Any phasors I calculate here, I cannot add or combine with any phasors I calculate here, right? Because they are in different frequency domains. What I have to do is I have to solve for them separately, but then I can still add them together. But then but before I do that, I have to go back to the time domain, where I can, in the time domain, I can add signals of different frequencies. Okay, so yeah, solving each part is easy. I1 prime is just going to equal what? It's going to equal 100 over 10 plus j10, and then I double prime phasor is going to equal 50 minus 10 degrees over 10 plus j20. Okay, so we can do the calculation. I1 I prime equals, if I do the math here, yeah, I end up with what? I end up with 5 minus j5, which equals 7.07 minus 45 degrees amp, and then I double prime equals what? It equals 1 minus 2 minus j2, that's 50 over 10 plus j20 times 1 minus 10 degrees. So the whole thing equals 2.24, that's the magnitude of this, right? And then the angle of this minus 10 degrees is going to be minus 73.43 degrees. Okay, so this is the phasor representation of I1, I prime, and I double prime. And then, so proposition says I should be able to add them together to get the total current. But then we said we cannot do that because they are in different frequency domains. So what we have to do is we have to go back to the time domain first. Then we can add them together. So I prime in the time domain is just equal to 7.07 cosine omega t, which is in this case 10t minus 45 degrees amp. And then I double prime t is just 2.24 cosine 20t. Now we are in the frequency is omega equals 20 minus 73.43 degrees amps. And then the total current I of t, right? So this current is going in this direction while this current is going in this direction. So the total current going in this direction is going to be I1 minus I2, right? It's going to be I prime t minus I double prime t. So the total current is going to be 7.07 cosine 10t minus 45 degrees minus 2.24 cosine 20t minus 73.43 degrees. Yeah, and that's this example. Okay, pretty simple. So now we're ready to talk about steady state power analysis. And we will start the discussion with instantaneous power. So you've covered instantaneous power in circuits 1, in networks 1. You know essentially that instantaneous power at any point in time is just the voltage times the current. That's what it is. And right, so watts, the units of watt equal volts, amps, right? And then there is the sign convention when calculating power. So power either in a circuit is either power for every element is either absorbed or supplied, right? So what determines whether power is absorbed or supplied, it depends on the on the sign convention, right? So if I have an element and my sign convention is as follows, V, and then the I is going in, right? Then when I calculate P equals VI, right? So this configuration of the signs and the arrows for the current designate an absorption, right? So this is B absorbed, right? Because the current is going into the element. So this is the P absorbed by the element, the power absorbed by the element. So when we use this convention and we calculate I and V based on this convention, if VI turns out positive, that means power is being absorbed. If VI turns out negative, that means in this case, with this sign convention, power is being supplied. Right? If we're using this sign convention, we have an element, and then our convention is that the positive current is going in this direction. So this is I and this is B. So in this case, when we calculate P, if we get VI to be positive, that means power is being supplied. If we get VI to be negative, that means power is being absorbed. Right? So what determines when power is absorbed or supplied by an element is not just the sign of the power. It's not just the sign of the power. It's the sign of the calculated power plus the sign convention in the circuit schematic. How does the polarity of V relate to the direction of I? Right? So for this convention, let me do this just P to simplify. For this convention, positive means absorbed, negative means supplied. For this sign convention, positive power, calculated power means supplied, and negative means absorbed. Absorbed and supplied are determined not just by the sign of the power, that's what I'm trying to say, but also by the sign convention on the schematic. Okay. So you've covered power for instantaneous power for DC circuits. The aim of this chapter is to understand how power behaves, or how can power be analyzed for AC circuits. How can power be analyzed in the AC analysis domain at steady state? We're still concerned only with steady state. Okay, so let's write down the equations, right? So V of t, in general, any general V of t in AC analysis is going to have this form in the time domain. It's going to be cosine Vm cosine omega t plus theta v, some phase angle, and then I of t equals Im cosine omega t plus theta I. Let's say the scenario is like that. We have this simplified circuit. We have some voltage source, we have some current, and this is going into an impedance. It doesn't have to be this. It's just, this is a simplified circuit to represent this. And the impedance will determine the angle between the voltage and the current. Okay. What is the instantaneous power in this case? P of t. It's just V of t times I of t, right? So this equals Vm Im cosine omega t plus theta v cosine omega t plus theta I. Now let's apply the trigonometric identity. So remember we said, hey, cosine phi1 plus phi2 equals what? Equals cosine phi1 cosine phi2 minus sine phi1 sine phi2. We also know that cosine phi1 minus phi2 equals cosine phi1 cosine phi2 plus sine phi1 sine phi2. I can easily add those two up. This cancels, plus minus, and I end up with 2 cosine phi1 cosine phi2 equals cosine phi1 plus phi2 plus cosine phi1 minus phi2. Right? This leads to this identity that cosine phi1 cosine phi2 is just equal to half the sum of the phis cosine phi1 plus cosine phi2 plus the subtraction of the phis cosine phi1 minus cosine phi2. So this is a very basic identity that we derived from this fundamental identity. Okay, so this allows me to go back here and rewrite this as two cosines, the cosine of the sum of those two and plus the cosine of the difference of those two. So what happens when I do that? I end up, first let me take out the common term. The common term is always going to be Vm Im, and then I have the 2, then I have cosine. Let me first take the difference between those two. Omega t cancels when I take the difference, and I end up with theta v minus theta I, or theta I minus theta v. Doesn't matter. Yeah, it doesn't matter because cosine is an even function, right? And then plus the sum of those two, so I end up with cosine 2 omega t plus theta v plus theta I. Okay, so this is the instantaneous power. Notice the instantaneous power has a constant term, right? Cosine theta v minus theta I is constant, it does not vary with time, while this is the AC term, right, of the power. The interesting thing about it is that this AC term has a frequency of 2 omega. It has double the frequency of the voltage and the current. Meaning the voltage and current, let's say, have 60 hertz, which is your typical wall frequency. The power term, the AC term of the power, is going to have a frequency of 120 hertz. The frequency of the power is double that of the line frequency. This is a very interesting phenomenon that has ramifications in AC power transmission and delivery. Okay, just plotting the power. You might have some voltage like this, right? Let's say you have some say the current is in phase, whatever, right? It doesn't matter. It doesn't have to be in phase. The power is gonna look something like this. It is gonna be double the frequency. Okay. So the question is, so this is the instantaneous power. The question that arises, this is a power that varies with time. The question is now, what is the average power? Over a certain period. So if I take the average power over this period or over this period, it should be the same, right? For any periodic signal, the average power over any period or multiple of periods should be the same. So the average power, capital P, is just 1 over the period, T0 to T0 plus T. It doesn't matter where I start. I just have to integrate for a whole period. So it's the integration of PT dt. It's the area under the curve of PT divided by the period. That's the definition of the average function, right? Or we can say that P equals 1 over NT. I can take multiple periods and should still get the same value. This is T0 plus NT capital, P of T, D of T. Okay, so what's the average power? We just have now to do the calculation, right? So that equals P equals 1 over T. What's T, by the way? T is 2 pi over omega. That's what T is, right? Omega T capital should be 1 period, which is 2 pi. Omega T capital equals 2 pi by definition, right? Because when instead of small t, if I put in 1 period, I should get an angle of 2 pi, because 2 pi is what determines the periodicity, right? The cosine and sine are periodic every 2 pi. Another way of seeing this is that omega is 2 pi f, so I end up with 2 pi f over 2 pi. I end up with 2 pi over 2 pi f. I end up with 1 over f, which is just t. Okay, let's calculate P. So it's going to be integration from T0 to T0 plus T of Vm Im over 2 cosine theta V minus theta I plus cosine 2 omega T plus theta V plus theta I dt. Now we could do the integration, but we don't need to. This part is constant. You can just take it out, right? So this part with the integrated for this will be 1 over T Vm Im over 2 cosine theta V minus theta I. So this is constant, right? So I can take it out of the integration. I'm integrating 1 from T0 to T0 plus T. I end up with T. So T cancels with T, right? But then also this part is a cosine function. A basic property of any cosine or sine function is that if you integrate them over one period or multiple periods, the integration is 0, right? Because the area under a cosine function or a sine function or a cosine function is 0, because you have equal amounts of positive area and negative area. Right? So this is a basic property of cosine and sine functions, is that when you integrate them over a period or multiple periods, you get 0. So this whole thing goes to 0. So I end up with the average power being half Vm Im cosine theta V minus theta I. If we have a case where the element we are examining, the power n, is purely resistive, what does that mean? That means that theta V equals theta I. That means because we end up with cosine 0, we end up with the average power being just half Vm Im. This is for a purely resistive element. If we have a reactance, what happens if we have a reactance? Then theta V minus theta I equals either plus 90 or minus 90, right? We're either leading by 90 degrees or lagging by 90 degrees. So we end up with half Vm Im cosine 90, positive 90 or minus 90. What's cosine 90 or positive 90 or minus 90? It's 0, right? So P equals 0 for reactive elements, meaning elements that are either inductors or capacitors. So that tells you that reactive elements, although they have instantaneous power flowing through them, do not have any average power flowing through them, meaning they do not absorb any average power or supply any average power. All that is happening with them in AC circuits is that over time and during some time they are absorbing some energy, some power, and over some other time they are supplying some power. So they are constantly absorbing and supplying power. Right? It's like a spring. The spring is constantly absorbing and supplying energy or force. So the same thing, a reactive element is constantly absorbing and supplying power, but on average, the power going through it is 0. That's a very basic property of reactive elements. Only resistive elements or resistive part of the circuit absorb average power, sorry. Okay, let's do an example. So we have this circuit, 10, 60 degrees, and I'm already assuming the frequency is known, and I'm calculating the impedances for you already. Right, so this is I going through the circuit. We have 2, and then we have an inductor with the impedance of J2. Okay. The question is, what is the, let's say, power supplied or absorbed by the source? So in this case, the sign convention is as follows. We have plus minus here, and then the current is going out. So any positive power calculated with respect to this voltage source is going to be power supplied, right? So what's I? I is going to be V over Z. V is going to be 10, 60 degrees over Z, which is 2 plus J2. I can do this calculation. I end up with 3.54, 15 degrees amps. Okay? And then I want to find the average power. So the average power is going to be Vm supplied by this voltage source is going to be supplied by this voltage source and absorbed by this. So there are two perspectives here. You can say this power is supplied by the voltage source, or you can say this power is absorbed by the impedance here. Okay, so this P is equal to Vm Im over 2 cosine theta V minus theta I. So this equals half Vm is 10, Im is 3.54, we calculated it here, the magnitude of I, and then cosine the difference between the angles of V and I. V has an angle of 60, I has an angle of 15 degrees. I end up with cosine 45 degrees, which is 1 over square root of 2. So I end up with 10, 3.54 over 2 square root of 2. And if we calculate this, we end up with 12.5 watts. Right. There is another way, another approach we could have taken. We know that the inductor absorbs no average power. So what we could do if we calculate the power absorbed by the resistor, we can figure out the whole power absorbed by the circuit, because we know that the inductor absorbs no average power. So if we calculate the power absorbed by the resistor, we can know the power supplied by the source, which is equal to the power absorbed by the resistor, because the average power supplied by the source is fully absorbed by only the resistor, not the inductor. Right? So to do that, we do P equals half Vm Im. But in this case, Vm is not the Vm of the voltage source. Vm comes from the voltage across the resistor. So we need to find first the voltage across the resistor and then use that in this equation to get the average power. Right? What's the voltage across the resistor? It's just a voltage divider problem, right? So we have 2 ohms over the total impedance times the input voltage. It's a voltage divider problem. So I end up with 2 over 2 plus J2 times 10, 60 degrees. I end up with 7.08, 15 degrees volt. Right, so now P equals half, because this is a resistor, there's no cosine. Right, cosine, the angle is the difference between the voltage and the current for a resistor is 0, so it's going to be cosine 0. It's going to be just half Vm Im. It's going to be half. What's the voltage across the resistor? 7.08. What's the voltage across the current through the resistor? 3.54. We calculated the current previously here. When I do this, I get the solution, which is 12.53 watts. So it is equal to what we calculated here, except there are some rounding errors. So this difference is due to a rounding error. You should expect rounding errors to happen when you do those sort of manipulations, unless you're very careful and consistent with how many. You're consistent with making sure you use a lot of significant digits. Okay. Now for a resistor, so I have Vm Im, the magnitude of the current and the voltage across the resistor. I have this form of the average power. But I can use Ohm's law to derive other forms. So Ohm's law says Vm equals Im R. So that leads me to other forms of this formula. So if I can plug in Im equals Vm over R, so I end up with half Vm squared over R. This is also a valid average power formula for a resistor. And then I have V, instead of Vm, I plug in IMR, I end up with half Im squared R. This is also a valid average power formula for a resistor in AC circuits. Okay. Let's do another example. Right? So we want to find the total power absorbed and supplied in this circuit. So we have a voltage source, and then I have I1, or let me call this I, and then I have two branches. So I have a 4 ohm, and then I have 2 ohms minus J. I have a capacitor. Then I have I2, I1, right? So I need to calculate the currents, right? So that I can find the total power absorbed and supplied. So I1 is just going to equal 1245 degrees over the resistance, Ohm's law, right? 4. This equals 345 degrees amps. And then I2 is just going to equal this voltage divided by this impedance, right? That's what it is, right? So it's going to be 1245 degrees. What's the total impedance here? It's 2 minus J, right? So this equals 1245 degrees over, I convert this to polar. I end up with 2.236 minus 26 degrees, 0.57 degrees. Right, let me just evaluate this. This is going to be 5.37, 71.57 degrees. Now the total I is just going to be, according to this circuit, is going to be I1 plus I2. So now I'm summing two polar form phasors. I just need to convert them to rectangular to sum them up and then convert them back to polar. So you can do this calculation easy now at this point. It's cumbersome, but it's easy and mechanical to do. So I end up with 3.819 plus J 7.2159, and then I convert it back to polar. I end up with 8.164 with an angle of 62.11 degrees. Finally, what is the power absorbed by the 4 ohm resistor? So in this circuit, I have a 4 ohm resistor. What's the power absorbed by this resistor? Is going to be just half Vm Im. It's a resistor, there's no cosine. So it's going to be half 12. What's I2? I2 turned out to be I1, sorry, I1 turned out to be 3. 4 ohms has I1 flowing through it. So it's going to be half 12, 3. This is going to be 6 times 3, which is going to be 18 watts. What's the power absorbed by the 2 ohm resistor? Right? This is going to be half, and I use this form of the power, Im squared R. So it's going to be half. What's I2? I2, we calculated it to be 5.37. The magnitude of I2. So it's going to be 5.37 squared times R. R is 2 ohms, right? Right, so this is going to be 5.37 squared, which is going to be 28.8 watts. So the total power absorbed by the circuit is going to be the power absorbed by the two resistors, right? The inductor does not absorb any power. So the total power absorbed is going to be 18 plus 28.8. So it's going to be 46.8 watts. What's the power supplied by the source? Power supplied by the source using this sign convention is just going to be I, times I magnitude times V magnitude with the cosine of the angle between them, right? Times half. So that's going to be half Vm Im cosine theta V minus theta I. In this case, Vm is going to be 12. Im is going to be the total current I, its magnitude, which is 8.164. And then cosine theta v is 45 degrees. And then theta I is 62.11, right? 45 and then 62.11. 45 minus 62.11 degrees. When I do the calculation, I end up with 46.8 watts. Of course, P absorbed needs to be equal to P supplied. This is a very basic property of circuits, is that energy is conserved, right? So any power that is supplied by any sources of the circuit should exactly equal any power that is absorbed by the elements in the circuit. Energy is conserved. Okay? One basic thing, now we want to do an example with multiple sources. One basic thing you have to remember when dealing with multiple sources is, we can use for V and I, we can use superposition, right? Superposition. We can set all the sources to 0 except one, calculate the response, and repeat that for all the sources, and then add them together. That applies for calculating any response, V or I. It does not apply for power, right? So superposition, so for power, superposition does not apply. You have to really keep that in mind, because if I have a circuit and then I can apply superposition to find a response due to two sources, but I cannot apply superposition to power calculations. I cannot say, hey, let me make this 0 and calculate the power absorbed, and then make this 0 and calculate the power absorbed, and just sum them up together. You cannot do that because power is non-linear. Power is proportional to V times I, or proportional to V squared, or proportional to I squared. It is not linear. I cannot just it doesn't have a linear form, so I cannot apply superposition to it. Superposition only applies to linear equations. All right. So you have to keep that in mind. I think you should have covered this point in networks 1. Just emphasizing that point. This point right now. Okay, so I want to do now another example with multiple sources. So I have source 12, 30 degrees. And I have multiple sources now. I have two sources. So I have I1, and then I have I2 that goes into a 2 ohm resistor. And then I have an inductor, J1 ohms. Then I have another source, which is 60 degrees. And I want to find the power absorbed and supplied in this circuit, right? So first I have to calculate the currents, right? So I2 is easy. I2 is just the voltage across it over the impedance, the resistance. So this is 630 degrees. So this gives me I2, and then I3 is simple too. It's the voltage difference across this inductor divided by the impedance of the inductor. So this is going to be I3 is just going to be 1230 degrees minus 60 degrees over the impedance, which is 1J. Right? So this gives me, let me convert this to rectangular and sum. This gives me 4.39 plus J6 over J. And finally, if I do this, this is equivalent to 190 degrees, right? If I turn everything now to polar, turn this to polar, and this is, we know what it's equal to in polar form, we end up with I3 equals 7.44 minus 36.21 degrees amps. Okay, so the only element that's absorbing any energy is the resistor, right? Average energy, average power. Right? We said we know that the reactance, the inductance, is going to absorb 0 average power. Yeah, okay. So what's the power absorbed by the 2 ohm resistor? That's going to be half VMIM. Do we know the voltage across the resistor? Yeah. Do we know the current through the resistor? Yeah. So we know VM and IM. So VM is half 12. IM is which is I1. We calculated it to I2. We calculated it to be 6. So it's going to be 12. Half 12 times 6 is going to be 36 watts. Okay. And then using this sign convention with I3 going in this direction. Yeah, I forgot to write that down. I3 is going in this direction. Using this sign convention, the absorbed power by the 6 volt supply is going to be whatever V voltage of the supply is times I3, right? So the power absorbed by this voltage supply, 60 degrees volts, is going to be half VM IM, right? Cosine, this is not a resistor, so we need to put the cosine theta V minus theta I. Okay, so we know half VM is 6, right? Why is VM 6? Because we know that the voltage of this supply is 6 volts. You know, it's a voltage supply, it fixes its voltage. And then the magnitude of the current is I3. I3 has a magnitude of 7.44. So it's 6 times 7.44. Cosine, what's the angle of the voltage? 0, right? What's the angle of the current? Minus 36.21. So it's going to be 0 minus 36.21 degrees. That's what the equation is going to be. So it's going to be 7.44 cosine 36.21 degrees. If I calculate this, I end up with 18.01 watts. Again, there might be rounding errors here. And then I want to find, so this is the total, this is the absorbed power. This is the power absorbed by the 2 ohms. This is the power absorbed by the 6 volts, 60 degrees volts. What's the power supplied by this, right? According to this convention, this seems to be power supplied because the current is going out of the source. So if I get a positive value for this power, that's the supplied power, right? So power supplied is just half VM. VM is 12 volts, right? I need to find I total. I total is I1, which is I2 plus I3. So I need to calculate that first. So let me calculate that. So I1 equals I2 plus I3. I2 is equal to 630. I3, we calculated it to be 7.44 minus 36.21 degrees. Right now, it's just a matter of converting each one of those into rectangular form and summing. I end up with 11.2 minus J 1.4. Turn it back to polar. I end up with 11.29 minus 7.1 degrees. So now the supplied power is going to be half V, which is 12, I, which is 11.29 IM. This is the magnitude of I1. And then cosine theta V. Theta V is 30 degrees, right? V is the voltage source has 30 degrees angle. I1, we discovered, has an angle of minus 7.1. So it's going to be 30 minus plus 7.1 degrees. Right? I just have to calculate this. So if I calculate this, I end up with 54 watts. Right? So absorbed power, so supply power equals P absorbed power, right? This is 54. This is equal to 18 plus 36. Notice I ignored the 0.01. This is just like a rounding artifact. So if you ignore the rounding artifacts, the supplied power equals the absorbed power. Now I want to introduce what's called maximum power transfer, right, in the context of AC power. Right, so you covered this concept in DC circuits, so you know that if you have some circuit that you can represent by its Thevenin equivalent, so you have V Thevenin, and then you have R Thevenin. So in terms of resistive circuits, right, the question is, how do I load the circuit? What kind of load do I add to the circuit such that I can guarantee that I get the maximum power transferred out of that circuit into the load? Right, this is a problem that you might encounter when you say that have, for example, some circuit that's like an amplifier, like a sound amplifier, right? So it's like in an audio system, right? And you want to connect speakers, right? The speakers, have a certain impedance, certain resistance, or speaker. So the question is, how do you maximize the power that goes into the speakers? Because if you maximize the power, you maximize the volume, right? The sound volume. And the point where you get the maximum power is when the R of the speaker equals the Thevenin equivalent resistance of the amplifier, R Thevenin. Right? That's a key concept in power. It's called impedance matching. Okay, right. So for DC circuits, we found out from last semester that R load must equal R Thevenin. What about the AC case? Now we want to cover the AC case. Right? What if we have our circuit that is now an AC circuit? So we have now a V Thevenin phasor operating at a certain frequency, and then we have a Z Thevenin, right? And then we have the load is an impedance, Z load, right? How do we maximize the average power going into the load? Right, so we have to go back into the equation. PL equals half VL IL. VL and IL as the magnitudes of the voltage and the current, right? Cosine theta VL minus theta IL. Now we know as phasors IL, this is IL by the way as a phasor. IL is just V Thevenin and this is VL by the way. Right. IL is just V Thevenin phasor over the total impedance, Z Thevenin plus ZL, and then VL is just a voltage divider, right? So it's just going to be V Thevenin times ZL over ZL plus Z Thevenin. And noting that Z Thevenin is just equal to R Thevenin, it has a resistive part and a reactive part, X Thevenin, and then ZL also has a resistive part and a reactive part, RL plus JXL. We can write the magnitude of IL as just the magnitude of V Thevenin, right, over the magnitude of Z Thevenin plus ZL. So this is the Thevenin plus ZL. So the magnitude of that is going to be the real part squared plus the imaginary part squared. So it's going to be R Thevenin plus RL squared plus X Thevenin plus XL squared, square root, and then VL, the magnitude is just going to be the magnitude of this, which is going to be the magnitude of V Thevenin. And then what's the magnitude of ZL? It's just going to be RL squared plus XL squared square root. That's the magnitude. Real part squared plus imaginary part squared square root. over the magnitude of ZL plus Z Thevenin, same thing as this. So it's going to be also square root of R Thevenin plus RL squared plus X Thevenin plus XL squared. And remember, the power equation also has theta VL minus theta IL, right? What's that? Theta VL minus theta IL is just theta ZL, the angle of the impedance. Why? Because impedance is just V over I, right? So the angle of V minus the angle of I is the angle of the impedance, right? So this equals theta ZL. But ZL is RL plus JXL, right? So what's right? ZL is it's the angle of ZL, but what's ZL? ZL is RL plus JXL, right? So what's cosine theta ZL? Right? Because remember the power equation has a cosine. So cosine theta ZL or cosine VL minus theta VL minus theta IL is equal. What's the cosine? Cosine is the real part RL over the magnitude. So it's going to be RL over square root RL squared plus XL squared. So it's time for us to plug everything back in. So PL equals half. What's VL? VL is, yeah, it's this term, V Thevenin square root RL squared plus XL squared over square root let me write it down. It's a lot to write down, but that's fine. And then this is VL, and then IL is this thing. So it's also going to be V Thevenin over the same thing. Right, so same. I don't want to write it down again. And then cosine theta VL minus theta IL, which is cosine theta ZL, is just going to be RL over RL squared plus XL squared. So this is going to cancel with this. With those two terms, the square root is going to go away. I'm going to end up with PL equals half V Thevenin squared RL over RL squared, sorry, RL plus R Thevenin squared plus XL plus X Thevenin squared. Okay, we want to maximize this. We want to find out what does the load need to be to maximize this. We're clearly here to maximize this. We need to make sure that, well, first we know that the reactive components do not absorb any power, right? But they do, in reality, they don't absorb any power, or you know, the average power going through them is zero, right? But they do affect the power that's supplied to the load, because we have this term here. So we want to remove this effect. How do we remove this effect? We make sure that this term is zero, right? How do we make sure this term is zero? We make sure that XL equals minus X Thevenin. So that's the first condition. Make sure that XL equals minus X Thevenin. When I ensure that, I end up with PL equals half V Thevenin squared RL over RL plus R Thevenin squared. This is exactly the same as the DC, the equation that arises from the DC analysis. So we don't have to repeat the analysis for this one. We know that the maximum power transfer from last semester is going to occur when RL equals R Thevenin, right? So this is the condition for maximum power transfer. ZL has to be equal to, which is equal to RL plus JXL, has to be equal to R Thevenin minus j x Thevenin, right? So in other words, ZL has to be equal to the Z Thevenin conjugate. Remember, the conjugate of the complex number is just taking the negative of the imaginary part. This is the, for AC analysis, this is the condition of maximum power transfer, right? ZL equals, it's an interesting formula, ZL equals the Z Thevenin conjugate. What about the special case where we have an AC circuit, V Thevenin, Z Thevenin, and then we just have a resistive load, RL. There is no X component. So under this, so this is the constraint condition where XL equals 0. Under this condition, when does the maximum power transfer occur? It's a special condition, it's not a general condition, right? Well, here we have to do the analysis. We rewrite PL as half V Thevenin squared RL over R Thevenin plus RL squared plus XL is 0, so we end up with X Thevenin squared. And then we use calculus, right? We want to find the maximum power transfer. Maximum power transfer, we find the point of maximum power transfer, we find it by taking dPL over dRL and equating it to 0. That tells me the peak. So if I plot PL versus RL, where TPL over DRL equals 0, that tells me where the peak of the curve is, and the peak of the curve is the maximum or the minimum. In this case, it turns out to be the maximum. So let's do this calculation as a review of what you guys already did last semester, right? So yeah, so 0. Let me differentiate this. This is just going to be half. This is a rational function. So it's going to be the denominator times the derivative of the numerator, which is going to be just V Thevenin squared, minus the numerator times the derivative of the denominator. That's a quotient rule. I'm applying the quotient rule. So the derivative of the denominator is going to be 2 R Thevenin plus RL, right? Over the denominator squared. So this is going to be over R Thevenin plus RL squared plus X Thevenin squared. The whole thing is squared. This denominator will not matter because I have a 0 here. It will go away. So multiply those two terms to the, send those two terms to the left-hand side, right? So they will be multiplied by 0, and I will end up with 0 equals this term, right? So I can say that 0 equals R Thevenin plus RL squared plus X Thevenin squared, V Thevenin squared minus V Thevenin squared 2 RL R Thevenin plus RL. I can cancel out V Thevenin squared, divide everything by V Thevenin squared, and I end up with what? Let me move this to the other side. I end up with plus 2 RL plus R Thevenin equals RL plus R Thevenin squared plus X Thevenin squared. Let me expand everything on the right and on the left. So I end up with 2RL squared plus 2RL R Thevenin equals, let me expand this. This is going to be RL squared plus R Thevenin squared plus 2RL R Thevenin plus X Thevenin squared. Clearly this cancels with this, right? Take this to the other side. This is going to be RL squared equals R Thevenin squared plus X Thevenin squared. So the condition of maximum power transfer FXL equals 0 is that RL needs to be square root of R Thevenin squared plus X Thevenin squared. So this is like a repetition of that basic analysis that you did last semester. It's an analysis that you take from calculus, where to find the maximum point, you just, the maxima or the minima, you just use calculus by differentiating and checking where the derivative goes to zero. Right? That's all this is. Okay, but for the most general case, where the load can be anything, can have reactive components and resistive components, this very simple formula tells you when maximum power transfer occurs. It occurs when simply the load equals the complex conjugate of the Thevenin impedance. Okay. All right. This concludes this lecture. See you next time.